Hello, Chem 1B. This is Chapter 20, Lecture Video 4, and we're going to talk a little bit about predicting the type of radioactive decay going on. Um, so why is an atom radioactive? Why is it unstable? Um, if it's unstable, how is it unstable? What's up? In the nucleus of any atom, as we all know, hopefully, is contained protons and neutrons. Now, the more protons an atom has, the more neutrons it needs to remain stable. If you think about it, like charges repel. So if we have a bundle of protons all really close to each other, why aren't those particles repelling each other and like breaking apart? Well, the answer is the neutrons. They kind of are the glue that holds the protons in the nucleus because they separate the protons enough from one another to where the repulsion between these protons is minimized. However, if your ratio of neutrons to protons is off from what is quote unquote stable, then your nuclei becomes unstable and it seeks to remedy this issue. So the neutron to proton ratio is an important predictor of stability. Now, as a general rule, any element with an atomic number greater than 83, bismuth, greater than bismuth, is going to be unstable. There are no stable isotopes at that high number of protons just because it's really hard to get enough neutrons to make that atom stable. This red line here is a 1-to-1 neutron to proton ratio. And as you can see, these blue, light blue and dark blue dots, this whole thing here are all the stable nuclei in our system. And as you can see, as we go up in proton numbers, the number of neutrons we need dramatically increases. However, as long as we're before atomic number 20, in other words, like calcium, most stable isotopes are found on a 1-to-1 neutron to proton ratio. Now, as we get above atomic number 20, it shifts to a little bit more neutrons per proton, as you can kind of see as this line begins to deviate from the 1-to-1 ratio line. This blue area, this thing I circled here, is what we call the valley or band of stability. These blue dots are all the different stable isotopes of nuclei at those atomic numbers, and the dark blue ones are the most stable and most high percentage of those isotopes present. Now, if you're above this valley, then the goal of this unstable nuclei, like this one, is to get back down towards the stable area. Now, if you're above the band of stability or the valley of stability, that means you have too many neutrons to be stable. You need to reduce the number of neutrons you have in your ratio and increase the number of protons. You can do that through beta decay. Whereas if you're down here, you don't have enough neutrons. You need to change some of your protons into neutrons to get that ratio back closer to where it should be. Now, that means that you need to do a type of radioactivity that will convert a proton into a neutron, which is one of two options: positron emission or electron capture. As you do these types, you'll get closer to the band of stability again. Now, as a rule of thumb for this class, there's a lot more that goes into predicting what type of radioactive decay you have. There are magic nuclei numbers, proton-neutron numbers. There's some rules with that. I'm not going to go into that. We're just going to assume that a 1-to-1 proton-neutron ratio is stable. And if you're above or below that ratio in terms of protons or neutrons, then you should be able to predict which type of radioactivity should be occurring to get back to that 1-to-1 ratio. And we'll just make that assumption for every type of problem that involves predicting radioactivity in this class. All right. So just a quick kind of cool thing. I think knowing how to detect radioactivity is pretty cool. So there's a number of ways to do this. One of the most common ways in a facility that has to deal with this, everybody typically wears what we call film badge dosimeters. It's basically a piece of photographic film. So kind of hard to see, but this little green label inside the plastic housing, it's a piece of film. And when it's subjected to enough radioactivity, it turns black. So you have your name on it. It's also your name tag. You need to be wearing it when you're in a facility dealing with radioactivity. They're pretty neat. I've never had one turn black on me, but I have had to wear them quite a bit in the research I used to do. So as soon as you see it turn black, you go, oh crap, gotta get out of here. We're being exposed to radiation. It doesn't tell you how much. It just tells you that, hey, once this thing turns black, we're in an area that is dangerous and we need to get out of there. The other ones are the more common ones. Everybody who've ever seen any type of sci-fi movie probably has heard of a Geiger counter. Geiger counters detect exactly how many radioactive particles are present, and it clicks when it's high radiation, right? So it'll like start click 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 if you like are in an area that has a lot of radiation. It also provides a numeric measurement for the dose that is present, how much radiation is present and how much damage that could be causing. Another type of Geiger counter, or really a counter of radioactive particles, is the scintillation counter. It also detects how many radioactive particles and can read exactly a quantitative number for how much radioactivity is present. These are both old-looking ones. I'm sure they have digital ones these days, but I couldn't find good images of the digital ones. So this gives you an idea of kind of how we can detect radioactivity, and I think that's important. But if you have any questions, as always. Now, we talked about kinetics quite a bit, so I'm going to fly through this slide. This is a review slide. One of the things that I mentioned very in like an offhand fashion when we were talking about kinetics, first chapter of the semester, is that radioactive decays are first order reactions. Now, that is something you need to know for this chapter. First order reactions means our rate law is rate is equal to some rate constant times a concentration. However, in our case, we use the number of radioactive nuclei for the concentration. K is our rate constant, N is the number of radioactive nuclei, and we know the half-life for a first order reaction is ln of 2 over K. And it's constant, so if you take 20 seconds for your first half-life, then it'll take another 20 seconds for the second half-life and the third half-life and the fourth half-life and so on. Meaning that if I have 1 million atoms of thorium-233, or 232, sorry, the half-life for thorium-232 is 14 billion years. So in 14 billion years from now, if I had 1 million atoms of these, I'll have 500,000 atoms. And in another 14 billion years after that, I'll have 0.25 million atoms of thorium-232. This is the half-life from thorium-232 to getting to the first stable nuclei. So there's number of reactions occurring here. But you get the idea. This 14 billion year half-life is staying constant. And each time we cut our amount in half, it takes about 14 billion years. By the way, the universe is only about 14 billion years old, so yeah, long time. So another thing you should know is the first order integrated rate law. And that is ln of, now we're going to use nuclei, radioactive nuclei at time t is equal to the natural log of your initial number of nuclei minus our rate constant times time. And so we're going to stop here for this lecture video. If you have any questions, please see me during my office hours or email me. I'm always happy to help.